So, welcome to the ECE Distinguished Lecture Series for, I guess, fall. Is it spring, fall, or not? Spring. This is the first in a series, and we are extremely honored and pleased to have Professor Onur Mutlu among us. So, we've known each other for a long time, and Professor Onur Mutlu is one of the most prolific computer architects out there today. So I'm going to read just a very brief little bio and then let him get going. So Onur Mutlu is a professor of computer science at ETH Zurich in Switzerland. He's also a faculty member at the CMU Carnegie Mellon University, where he previously had the Stecker Early Career Professorship. His current broader research interests are in computer architecture systems, hardware security, and recently he's dabbling in bioinformatics, leading the charge again at the forefront of development. So, a variety of techniques along his group and the collaborators he has invented over the years that influenced industry and have been employed in commercial microprocessors and memory storage systems. He obtained his PhD and MS in ECE from the University of Texas, Austin, and the BS degrees in computer engineering and psychology from the University of Michigan, Ann Arbor. So these are big powerhouses in computer engineering and ECE, both Austin and Michigan. He started the computer architect group at Microsoft Research and held various product and research positions at Intel, AMD, VMware, Google, and name it. Literally everything in the industry. He dabbled in. So he received the inaugural IEEE Computer Society Young Computer Architect Award. This is extremely competitive, very, very prestigious, and established by the IEEE Computer Society. And he was the very first one to get this one. And the inaugural Intel Early Career Faculty Award, another very extremely prestigious award, and of course the U.S. National Science Foundation Career Award at Carnegie Mellon University. I think I'm not going to keep talking about all these awards. We'll be able to hold. There's a long list of awards. He's one of our most prolific scientists in computer architecture, and we're really, really pleased to have him here. And by the way, just to plug in a plug for HPCA, this week, starting from tomorrow, Saturday, the 16th to the 20th, is the most premier conference in computer architecture taking place here in Washington, D.C. It's HPCA 2019, the 25th anniversary of HPCA. Professor Guru and I are the general chairs. And if you happen to have some time between now and the 20th, please stop by. Don't worry about registration or whatever like that. Just with Professor Guru and just walk in there and see the talks and what have you. Okay?
Okay. Thank you very much.
Pleasure, Professor.
I really appreciate the introduction. Is this good?
Yeah.
Okay, there's no echo. Okay, it's a great pleasure to be here. Thank you for the invitation, Ahmed. And, I definitely recommend, if you're interested in architecture, I would definitely recommend that you go to HPCA. It should be fun. Okay, so when Ahmed invited me, he said, you have 1 hour. I'll try to stick to that. But this is a much longer talk, actually. So we'll skip some slides, don't worry. Hopefully you'll get the gist and insights of everything. Feel free to ask questions also. And I believe there's a reception after this. We can ask questions during that time also. So I'm going to talk about, there's some echo, I think, but slides. Okay, maybe I'll put it down. Is this better? Okay. Okay, I'll talk about processing in memory, or processing data where it makes sense, enabling in-memory computation. But I'll first start with what we're dealing with, which is the main memory system. If you look at a system today, we have the main memory system as a big component of the computing systems that we design. And whatever system you're designing, you have to have some sort of main memory or working storage. Server, mobile, embedded desktop, sensor, you have to have this working storage. And this is a big determinant of your performance, efficiency, cost, and many different things. And this system, main memory system, must scale in different ways in terms of its capacity or size, technology, efficiency, cost, and the algorithms we use to manage it if you want to maintain the performance growth and the technology scaling benefits that we've been used to for a long time. And it doesn't matter what you attach to this main memory, processors and caches, FPGAs, GPUs, or a heterogeneous integration of these different devices. We're bottlenecked by this interface to main memory today. And what kind of performance or efficiency we're getting out of main memory is dictating our system performance. And I'll give you examples of this throughout this talk. This is another example of the memory system in my little drawing. Actually, I had submitted this as part of my NSF career proposal a long time ago. It's still the same figure. Essentially, if you look at a system that we designed today, cartoonish of course in this case, most of the system is dedicated to store elements that store and move data. So only these red parts are cores that are doing computing. And even in those red parts, you have a big chunk of the architecture that's dedicated to storing and moving data. Register file, interconnects, L1 caches. So we're designing these systems, but most of the components are, this is not working very well. If you don't mind, I'll switch to another one so that you can see what I'm focusing on. So,
In Switzerland, this is USA.
I see. It's supposed to work, right? Yeah, so if you look at this picture over here, most of the system is really dedicated to storing and moving data. Computation is a very small part of the system. That's one of the takeaways over here. In fact, if you actually do the calculation, more than 80 to 90% of the system is really dedicated to data storage and movement elements. Caches, interconnects, memory. If you go out over here, that's better. Other interconnects, other storage parts. So we're calling these computing systems, but most of the time, most of the resources are really dedicated to data movement and storage, not computation. In fact, computation is the little part today, easy part today. There's another aspect of this. This system, the memory system, is a shared resource across these different computing units. I'm not going to tackle that, but this leads to predictability, quality of service, and latency issues, which we're not going to talk about. So let me tell you in one slide the state of the main memory system as I see it today. Today there are some recent technology, architecture, and application trends that lead to some new requirements from the system and exacerbate old requirements. And we've always demanded a lot from the system. We're demanding a lot more today. I'll show you examples of this. And I will posit and hopefully show you that the main technology we use to construct main memory with DRAM, dynamic random access memory, and the memory controllers, as we know them and as we design them today, are unlikely to satisfy these requirements. In fact, they're already failing to satisfy these requirements. And there are some emerging memory technologies that happen to be non-volatile that enable new opportunities. Phase change memory is one example. Intel's 3DX points, which is likely phase change memory, is another example. And these enable some opportunities like merging of memory and storage. I'm not going to talk about this part as much, but keep this in mind because some of the things that I'm going to talk about can be done very, very efficiently in these emerging memory technologies. So given these trends, we need to rethink the main memory system and the systems we've been designing around this memory system for a long time to fix the issues we're having with the DRAM technology and enable emerging technologies, while of course satisfying all of the requirements. So let's take a look at what are those trends and requirements that we have in main memory today. In one slide, this is the summary. There are three things. One is there's an increasing need for main memory capacity, bandwidth, and quality of service. And I think I don't need to motivate it. If you just look at how much memory you have in your cell phone, it's been increasing. And we will see that example, not from a cell phone, but from the chip perspective, right? And the bandwidth and quality of service. So let's take a look at this. This is really driven by three things. One is certainly applications. They're very data intensive today, and it's going to be increasingly data intensive, and this is a very good example of this, I will say. And computation is not a big problem. We were able to actually put many cores on a single chip. We can actually integrate many, many computation agents. This is easy. And once we put them on a chip, they're going to demand more capacity, bandwidth, and quality of service. And we want to consolidate more and more. Basically, in every system that we design today, we want to put multiple applications together so that we can improve efficiency. And these are driving the capacity, bandwidth, and quality of service or performance requirements on. So this is one example. I'm not going to spend a lot of time on this, but this is a paper that was written in 2009 by HP Labs at the University of Michigan, where they showed that core count is increasing much faster than memory capacity. And this is because it's easier to scale the core count. Memory capacity is not easy to scale. As a result, there's a gap in terms of how much capacity you have per core. And memory capacity per core is expected to drop by about 30%. And this is not good because software has always relied on having more memory capacity on a given thread so that you can add more features. So if this trend continues, we'll have difficulties in designing software. And actually, trends are much worse for memory bandwidth per core. I'm not plotting them here. Actually, I give this as an assignment to my students in the courses. But if you actually do the calculations over the years, memory bandwidth throughput has increased by about 10% every year, which is much lower than the memory capacity actually. So let's take a look at this from the DRAM perspective a little bit. This is, we're going to study the DRAM devices of the day, DDR devices, the most common devices, commodity devices in the last 18 years. And we're going to normalize to 1999, and we're going to look at the improvement that we've seen in the chip in terms of capacity, bandwidth, and latency. How much do you think capacity has improved over the last 18 years? Any guesses? Any bold person?
Computer architects in the room.
Yes, please, computer architects. Do you say any number? 10x I heard, I'll take it. It's actually much better, under 28x. So capacity has been improving, and this is actually the major goal of manufacturers today, because we want to increase capacity because applications are very data intensive. But as you see, it's not as good anymore. It's not the exponential trend. We're struggling with the exponential trend now, and we will see examples of why that's the case. What about bandwidth? It's basically about 20x. It's improved a lot, but it's not improving as much anymore because of power limitations and other things. What about latency? It's flat, basically. It is actually flat. It hasn't improved that much. So we're going to have problems with latency going forward. So today, chips are designed for capacity, but even with capacity, we're having problems. It's not improving as fast because of scaling, technology scaling issues. Bandwidth is not very good, but it's going to get better maybe with 3D stack technologies, but only one step function maybe. And latency is something we should probably focus on. And I'm not going to talk about this today, but there's a lot of opportunity in improving memory latency going forward. So clearly, memory is critical for performance. These are some applications that are really interesting, I think. And people have studied and shown that essentially memory is a big performance bottleneck. That's true for some of the other mobile applications. If you look at the mobile side, I'm going to give you more examples from these particular applications later on. Memory is a performance bottleneck.
Since you asked us, we can ask
Sure, yeah. If you can keep it quick, yes.
All of these is off-chip, right? You're not talking about on-chip.
That's correct, yes. I'm talking about the off-chip DRAM right now because of the bottleneck between the chip and the memory. We have this interconnect bottleneck. On-chip memory, there are caches. Some of them are actually bottlenecked by caches also, but we can scale them much better right now. Yeah. Okay, so let's take a look at the other trend, which is energy and power. And energy and power of memory is a key system design concern today. This is data that was published by IBM in 2003 or so in their servers, big iron servers. They found out that more than 40 to 50% of the energy is spent on the off-chip memory system. At that time, in 2000 or so, it included the off-chip DRAM, off-chip caches, off-chip storage, off-chip interconnect. Okay, fast forward about 10 years. IBM published another paper on Power 8, the state-of-the-art system that they had at the time, and they say more than 40% of the power is just in DRAM, because that's the major component of chip, and it's spending more than 40% of the power. That's true for the GPUs as well. So we have an increasingly bigger problem in terms of memory power. And one of the issues with DRAM is it consumes power even when it's not used. You need to periodically refresh it, and this is actually a scaling problem of DRAM. So we've done a bunch of studies in memory. I'll give you one example of this. This is a paper that we have recently written in ASPLOS. We worked with Google to understand these mobile workloads that they have in the system. And average across the workloads that we studied, Chrome browser, for example, the TensorFlow inference and learning engine, and the VP9 video encoder and decoder, which is heavily used in a lot of applications. More than 60% of the entire mobile system energy is spent on the data movement across the memory hierarchy. Okay, we'll get back to that number. So the third major trend, on top of all of this, we need more from memory, but memory is not giving us more. Basically, technology scaling is ending from the DRAM side. ITRS, International Technology Orbit of Semiconductors, they've been projecting for a long time that DRAM will not scale easily below an X nanometer feature size. Of course, they don't say X. They keep changing their predictions. That's why I keep X over here so that I don't keep my slide coherent with their projections every time. We're going to get back to that X. But clearly, as you reduce the feature size of a DRAM cell, you get benefits. What is the benefit? You get higher capacity, higher bits per area, you get lower cost, and you get reasonable, if not lower, energy scale. And if this goes away, if we have difficulty scaling, reducing X, then all of the benefits will go away, and we're going to be at a very difficult place to satisfy these requirements. So we'll get back to the scaling issue. Let me give you examples of this already. Basically, it's difficult to significantly improve DRAM capacity and energy. As a result, today we have a proliferation of different memory technologies. Some of them are DRAM-based, some of them are not DRAM-based. Let's take a look at some of them. There's 3D stacked DRAM. You have a logic layer underneath memory layer. You get very high bandwidth through silicon vias. There's reduced latency DRAM today that's very expensive. I think going forward with some of the ideas, it's going to be less expensive. The low power DRAM, actually a lot of the DRAM is going to be low power. And there's non-volatile memory, of which there are many, many different types, as you can see over here. So you get larger capacity. I don't want to go into the details of this, but what I want to point out is all of the memories have different greens over here. These are the most salient greens, meaning the good parts, but they also have reds. Meaning that there's no single memory technology that seems to be out there that's going to satisfy all of our requirements at the same time. So as a result, what do? You basically become more heterogeneous in the memory hierarchy. So people are now going into designing these heterogeneous memory systems where you have different technologies put together. Different technologies have different greens and different reds. And the goal is to design a system such that you have the hardware and the software that manage data allocation and movement intelligently to achieve the greens as much as possible while avoiding the reds as much as possible of all technologies. So this is actually a very nice field, nice area. I'm not going to talk about that. But clearly, one thing that you need in this case is you need to have an intelligent memory controller. So if you want to actually understand what data should be here and what data should be here and when they should be moved from one to the other, your memory controller needs to be intelligent. If you actually do this completely in software without any memory controller support, it's a lot of overhead. Then you don't move the data. You'd better keep it in one technology. So I'm going to motivate the need for intelligent memory controllers over and over until we get to the processing in memory. Okay, so it's actually not just us that are talking about this. The industry is writing papers about it too. If you really want to read one paper in the area, I would recommend this paper. It's a 4-page paper that was written by 2 companies that don't otherwise talk to each other, Samsung and Intel. And I think this is the only paper that I've seen that was written together collaboratively by these 2 companies. We invited them to write for the Memory Forum. It's a 4-page paper. They talked about basically DRAM process scaling challenges. They basically said we're having difficulties scaling DRAM to smaller technology nodes. Refresh is a problem. I'm going to talk briefly about that. It's very difficult to determine the retention time of a DRAM cell today. Because what happens is one of the issues is variable retention time. A DRAM cell, when you test it at this point in time, it may retain data for 100 seconds. It may look strong. But when you test it later, it may retain data for only 8 milliseconds. Why does it happen? Because charge randomly gets trapped in the access transistor. And once charge gets randomly trapped, this is not a controlled process, the charge from the capacitor drains very quickly through the access transistor. And you cannot control this. It's a random process, and you would like to determine how frequently you need to refresh DRAM in the presence of this random process. That's very difficult. And they basically say in this paper, and we also experimentally demonstrated before this paper, that this is becoming a much bigger issue in DRAM today. So we need to actually somehow have a solution. And the solution that they propose is going to be very similar to what I'm going to advocate. Basically, you want to have intelligent controllers that understand how the circuit behaves and overcome the deficiencies of the circuit by, for example, adapting the refresh rate. We'll talk about some of the solutions with some examples in a little bit. So industry is also talking about intelligent memory controllers going forward because it's not easy to have a reliable memory technology today. Okay, so this is the outline of what I have. We don't need to cover all of it. Basically, I'm going to motivate intelligent memory controllers from the bottom up, from the circuits and devices perspective. I've already given that flavor to you a little bit. I'm going to go a little bit deeper in this area because the problem is actually even more serious than what I described so far. And then I'm going to motivate the problem from the top down. You need intelligent controllers from the applications perspective also. And I'm going to motivate processing in memory from that both perspective. We're basically squeezed in the middle right now. We need to have processing in memory somehow, or minimize data movement. And then I'm going to hopefully talk about 2 different directions, flavors of processing in memory. Minimally changing memory chips by adding analog computation inside them, and exploiting 3D stacked memory where you have a logic layer underneath the memory layer to do more general purpose processing in memory. I don't think we're going to have time for the adoption, and hopefully we'll have time for the conclusion because that's the most fun part of the talk actually. Okay, so I'll start with this actually. Basically, what should we start with? This is a person who's a very famous American psychologist. How many people know him? I have a side channel here. Okay, that's great. So a lot of people know him actually. This is Maslow. Hopefully you knew it before you saw the side channel. The name is over there. So he's more famous for this. Basically, he dedicated his life to understanding why humans do the things they do. Why are they motivated? And basically he came up with this pyramid of needs where he said you first need to have your safety, security, and physiological needs satisfied before you can think about love and self-esteem, and then before you can think about highest forms of abstract arts, right? So that's why we need to start with reliability and security. And today, I think, because of the changes in memory technology, our reliability and security is threatened. It's another example that I use in my classes when I motivate security and reliability. Does anybody know what this is?
The Coleman-Narrows
The Coleman-Narrows bridge, exactly. This bridge doesn't exist as it looks like in this picture because it was actually, this is what happened to the bridge basically, 6 months after it was constructed in 1941. So it was a reliability problem because of aerostatic flutter. Over here, it collapsed. And it was a safety and security problem. Also, actually, if you look into the history of bridge incidents, this is actually a lucky incident over here because only one dog was the fatality here. And there's an interesting story, but I don't have time to go into the story right now. Okay, so why do I show you this? Basically, we're at this situation in technology today where a single bit flip may actually cause a lot of reliability, safety, and security problems. And I'm going to talk to you about that bit flip. But I'll give you one other example. These folks who are constructing Manhattan are very happy right now, but if a single bit flip happens over there, you can think about the consequences. And you can generalize this. This thing is the bridge over here right now, but if it's a self-driving car, it's the same thing, right? It's so fundamental. Okay, so basically, let's pull back to the DRAM scaling problem. So I was talking about the DRAM scaling problem. Like any other technology, DRAM needs a storage device and an access device. In DRAM, the storage device is the capacitor, access device is the access transistor, bit line, and the sense amplifiers. And for any technology to work, both of these devices need to work. For DRAM, the capacitor must be large enough for reliable sensing, and the access transistor must be large enough for low leakage and high retention time. As we reduce the size of the circuit, both of these properties become very difficult to maintain. And we're at a point where we're unable to maintain these easily. And this was the value that was assigned to X in the previous slides by ITRS in 2009. They said scaling the size of the feature size of the circuit below 35 nanometers is challenging. How many of you know what is the feature size of a DRAM cell today? Cutting edge DRAM.
10.
It's not 10. You're optimistic. That's good though. We're about 16, 17 nanometers. Clearly we're below 35 nanometers because manufacturers pushed it down because they're driven for capacity. That's the only thing that's in their minds right now, right? But this came at a cost. So this is one example. This is a study that we did with Facebook. Basically, we analyzed all of the memory errors that they have in all of the data centers across the world. There's actually a lot of memory errors, a lot of memory, a lot of servers. They don't allow us to publish the number because that affects their stock price. But they should probably be concerned more about other things related to their stock price right now, rather than the size of their fleet. But basically, the takeaway is, if you do this correlational study across the entire real system, you see a very strong correlation between the chip density that's employed in the system and the failure rate that you see in the servers. So there's a very strong correlation, as you can see over here. And the intuition is that you get a quadratic increase in capacity. As you increase the size of the chips, cells are much closer to each other. They're more vulnerable to bit flips. As a result, you get more errors in the field. This is a very interesting paper. I'm not going to go into more detail. There's a lot more data that we've published in about 2015. So we've also been studying these bit flips or different kind of error mechanisms in DRAM using our FPGA-based infrastructures. This is an FPGA-based memory controller. This is actually the first incarnation where we actually made up something to actually heat it up and cool it. Essentially, we tested these different bit flip mechanisms. I'm going to tell you stories about some of these mechanisms. This is another recent one. This is one of the more recent ones. We actually released this in HPCA 2 years ago. You can do these studies using a C++ programmable memory controller. You can replicate all of the studies that we've done, and some people have done that actually. So if you're interested in using this, we'd be happy to support it. So some of the things that you can figure out if you actually build an infrastructure like this is the retention time profile of DRAM cells. So today we're refreshing every DRAM cell every 64 milliseconds. That's causing the power consumption here in this cell phone right now. But if you look at the retention time profile of DRAM cells in a DRAM chip, it's very heterogeneous. Most of this, because of process variation, manufacturing variation, most of the cells don't need to be refreshed every 64 milliseconds. You can get away by refreshing them every 256 milliseconds. So you can actually, if you know this profile information, you can get rid of 75% of all of your refreshes, which is a good chunk of the power consumption. And refresh is one of the big scaling problems in DRAM. So of course it's not that easy. It turns out this profile is not static. It's dependent on the location. It's dependent on the value pattern that's stored in the cells and the cells around it because of capacitive coupling. And it's dependent on time because of the variable retention time that we discussed. So this is very interesting, but if you really want to exploit this, you really need to have an intelligent memory controller that understands how often you need to refresh different cells. So that's another example where we need intelligent memory controllers. Let me give you one final example. So while we were actually doing the studies that we were doing, we stumbled upon an error mechanism that's very interesting, which is the fact that you can actually, if you buy a chip in the field today, you can predictably induce errors in most DRAM memory chips that you buy. This is called the DRAM rope hammer problem. It's a simple hardware failure mechanism that can create a widespread system security vulnerability. I think of this as a bridge, Tacoma Narrows bridge. If you get a bit flip, the bridge falls. And people are writing articles on the web like this, forget software, now hackers are exploiting physics. I like this because it's really talking about the problem. So what is the problem? So if you take a DRAM chip, you may try it in your laptops if it's old, especially right now. Basically, if you want to read a cell, you need to activate the entire row. Memory consists of rows, you need to activate a row. What does activate mean? You need to apply high voltage to that row. Now let's assume that you apply low voltage to that to do something else later. So that closes the row. Now if you do this repeatedly, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, or activate pre-charge, activate pre-charge, activate pre-charge, it turns out in most modern DRAM chips, physically adjacent rows get bit flips. So by just reading a memory row, you're inducing bit flips in adjacent rows. This is not supposed to happen because whenever you read memory or write to it, you shouldn't change anything. So we call this the hammered row, we call these the victim rows, and we showed that you could actually induce these disturbance errors, row hammer errors, in most real DRAM chips. What is most? We tested a bunch of chips from different manufacturers, there are 3 of them, 3 major manufacturers at least. More than 80% of the chips that we've tested are vulnerable to this problem. And whenever you induce an error, you can induce the error again and again and again. So it's very predictable. If you can flip a bit, you're going to flip that bit again and again. Okay, so why is this a scaling problem? Because this problem didn't exist before, at least it wasn't exposed to the users. All of the chips that we tested that were manufactured before 2010 didn't have this problem. The first occurrence happens in 2010. And all of the chips that were manufactured between 2012 and 2013 that we tested actually are vulnerable to this problem. Okay, so why is this happening very quickly? Because cells are too close to each other, you have electromagnetic coupling, that's one of the reasons. Whenever you activate one row, you're slightly activating the adjacent row also. And if the cell is vulnerable, you're leaking charge little. If you do this activation many, many times, you're leaking charge little by little every time you do the activation. If the cells don't get refreshed frequently enough, you actually deplete the charge from a vulnerable cell. That's the error, one of the error mechanisms. Okay, so why is this interesting? So this is clearly a reliability problem. Real programs actually do this, but not very often. But it's also a security problem, because you can actually write a program that looks like this, that has 6 lines. We released this code, that selects addresses X and Y, such that it basically avoids the cache, avoids the rows, and basically does this. Ping-pongs accesses to rows X and Y in memory. And if the chip is vulnerable, it's going to induce errors over here. You can actually download this code from our repository and test it. I would recommend backing up your machine before doing that. Yes?
But if you refresh, you get back the bit.
Exactly. So,
why is it fast?
because today, refresh intervals are not frequent enough to avoid the problem. It's 64 milliseconds is not enough, basically. So today, actually, so this is our code. Google Project Zero later took our code. They were intelligent based on some observations in our paper. They actually selected addresses X and Y such that they sandwiched one row in between, and they hammered in between. They call double-side row hammering. So you can actually do 40,000 activates and induce bit flips. And that's 64 milliseconds give you a lot of time to be able to do 40,000 activates. So one solution is increasing the refresh rate. Actually, I'm going to talk about that, but that's not a good solution because refresh rate is not good for energy, performance, quality of service, anything. Yes.
Are error correction codes used to?
So error correction codes get rid of a good chunk of the problem, but we see you need strong error correction codes to actually avoid all of the problems. So we see as many as 4-bit flips, and as technology scales down to even smaller feature size, we expect that you'll get many, many more bit flips in a single row. Okay, so this is data from 2014. Basically, we tested this on Intel and AMD chips, and we showed that as long as you have a memory controller that's good enough in accessing memory fast enough, you can actually induce errors. There's nothing special about Intel and AMD. Later, people showed that IBM, ARM, you can do it on any chip, basically. Yes?
Good question. Why do you think
Oh, okay. That's just to make sure that the ordering is nice. Actually, you may not really need it in some processors, but we actually did that so that the ordering is nice to control the experiment, basically. Okay, so this is actually a bigger problem than it looks. Basically, when we first wrote the paper, we said that memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. I still believe that firmly. And we said that you could actually design an attack that could take over the system. And while we were doing that, the good folks from Google Project Zero posted a blog post in 2015 where they said that they did exactly what we suggested. You could exploit this DRAM rowhammer failure mechanism to gain kernel privileges. I'm copying and pasting directly from their blog post over here. If you're really interested in hardware security, I would recommend reading this blog post. It's beautiful security engineering. They basically took the bit flip and took advantage of it. So how do they do it? They basically learned the problem from our work. They tested a selection of the laptops and found that the rowhammer problem existed. And they did 2 working privilege escalation exploits. One of them is very interesting. It basically induces these rowhammer bit flips to gain kernel privileges on an x86-64 Linux when you run this as an unprivileged user level process. And the idea is, of course, there's a lot of security engineering that's behind it, but the idea at the high level is you induce bit flips in the page table and the entry of the process that points to its own page table. And if you actually change the permissions by flipping the right bits in the page table, you can gain write access to your own page table. And once you gain write access to your own page table, you basically circumvent any security mechanisms, right? You can read-write the entire physical memory at that point and get root privileges. It's fascinating, I think. It's beautiful engineering. And this became famous as the rowhammer vulnerability. People started drawing pictures like this. And is it the end of memory? I like this particular thing. This is a very famous hacker on the internet. He described rowhammer as, it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. It's nice, actually. Okay, so this is very interesting. There's a lot of literature on it. I'm not going to go over this in detail, but these are some interesting papers. This is from TU Graz, where they showed that you could induce these rowhammer using remote software-induced attacks through JavaScript and take over the systems of website visitors. This is another interesting one. You could probably download this application if you have an Android system, where these folks from Vrije University in Amsterdam, they showed that you could exploit the deterministic memory allocation patterns in an operating system to fool the operating system to allocate a page table entry in a location that you know is vulnerable to rowhammer, and then rowhammer that location and then gain kernel privileges and basically take over your cell phone. And they do it deterministically because of the deterministic memory allocation patterns in the operating system. This is beautiful, actually. And later, people showed that you could do it through the GPUs much more efficiently, and then you could do it across the network through the RDMA, Remote Direct Memory Access Interface, and even more to come. Maybe this is one of the other attacks that will come later to fix the problem. I don't suggest this is the solution to the problem. But what is the solution to the problem? As Ahmed mentioned, refreshing more often could actually help, and that's essentially what industry is doing right now, because there is not enough programmability, not enough intelligence in the memory controllers today. Memory controllers, you can change the refresh rate, and Apple released a patch where they said rowhammer is a problem, we mitigate it by increasing the memory refresh rates. And they were nice enough to actually cite our paper in their security release. That's why they're on the slide. Other manufacturers employ exactly the same solution, but they're not on the slide. Okay, so I think refresh is, of course, the solution that's easy to do in immediate chips. We can talk about solutions, but we don't have time. I'll give you our solution. It requires changes to the memory controller of the DRAM chips. It's basically a very simple solution. It's very probabilistic. After you close a row, you activate the adjacent rows with very low probability. Let's say 5 out of 1,000 times. And if you do that, you get a very strong reliability guarantee. You don't refresh the entire memory, you just activate the adjacent rows with very low probability. So you get very good protection at very low cost. You don't need actually any state, you just need counters, 2 counters. So it's low cost, low complexity. So this is actually interesting, and this is actually currently implemented in some DRAM chips. It's not exactly in the way we proposed. What they do is, they actually exploit the timing slack in the refresh parameters. In DRAM, there's this interface where time is specified, and there's a lot of slack in the timing interface, so they can actually sneak in some refreshes in that. But it's not a good solution, I think, because we want to get rid of that slack to reduce latency. So we implemented the memory controller. This requires better coordination between the memory controller and the DRAM, and it requires memory controller to know which rows are adjacent. That information today is not exposed to the memory controller. So this requires slightly intelligent memory controllers, basically. But the good news is industry is open to doing that. This is actually one of the recent Intel machines. In the BIOS, you can pick your rowhammer solution, You could pick the hardware row hammer protection or 2x refresh. And what is hardware row hammer protection? It's essentially probabilistic adjacent row activation. With some probability, you can decide after how many activates you're going to refresh the adjacent rows. So the memory controller actually employs this. Does it always work? You can check it out. There's actually a lot of literature on row hammers. You can actually contribute to it if you're interested. Okay, so I'm not going to go into more detail over here, but there are more issues coming up in terms of reliability. Row hammer is a serious example, but I believe it's not the end of the examples. And as I said, industry is writing papers related to this, and they're proposing solutions that are similar. You need intelligent memory controllers. So we actually have these intelligent memory controllers, but in a different technology. In flash memory, for example, you have very similar reliability issues, actually even worse reliability issues. But flash memory doesn't suffer from these issues because it has an intelligent memory controller protecting it. Intelligent memory controller does a lot of optimization in terms of voltages, error correction, other things to actually fix the errors such that they're not exposed to the system. And if you're really interested, we have recently written a paper that summarizes our research in the last 8 years or so that talks about how you actually do these error corrections in flash memory-based solid-state DRAMs. So the takeaway is, in DRAM, we need intelligent memory controllers to fix the reliability problems that we're having from the circuits today. So let me pull back to the top-down approach. So that's the circuit push. We actually have a pull from systems and applications also. If you look at the system and application side, data access is a major bottleneck today. Energy consumption is a key limiter, and data moment energy dominates compute. I'm going to cover these relatively quickly first. So clearly we need more memory performance. There are applications that need more memory performance. And from my perspective, the question is, do we want something like this in the future, very beautiful Switzerland, or 1940s Pittsburgh? Your choice. I think we don't want that. All right. I like Pittsburgh actually. There's nothing against Pittsburgh. This is just a picture that was that was true in 1940s. So okay, if you actually go back and deconstruct what I said earlier, Maslow didn't say reliability and security are the most important things. The most important thing is you need to have energy to live. Right? And then you may need to worry about reliability and security. That's why this is very important. We need to be energy efficient, but at the same time, we need to be high performance and sustainable. So the problem is data access is the major performance and energy bottleneck that we have in systems today. But our current design principles completely go against it. They cause great energy waste because they cause a lot of data moments between the processor and the memory. As a result, they also cause a great performance loss, but I put this in parentheses because systems today try to hide that performance loss a lot. We build these cache hierarchies, prefetching mechanisms, multi-threading mechanisms, heavy out-of-order execution. We're trying to overcome that performance loss, but we're actually adding more to the energy waste by adding all of that additional circuitry. The fundamental problem is processing of data is performed far away from the data. If you look at a computing system today, this is one line of seminal paper. It consists of computation, communication, and storage and memory. And today we've optimized this computing unit significantly. Today's systems are overwhelmingly processor-centric. All data is processed in the processor. It has to go there to be processed. And processors, as a result, is heavily optimized and is considered the master. And data storage units and the communication units mostly are dumb. They're largely unoptimized. They cannot do anything to the data. Yet, let me give you the picture, the performance picture. This is a quote from Dick Seitz, who was the chief architect of Alpha 21-264, which was the fastest machine of its time. After designing this machine, he wrote this beautiful one-page article where he said that we designed this machine such that it can finish 4 instructions every cycle, which was really a lot at that time, but it's finishing only 1 instruction every 4 cycles. So it's operating at 1/16 of its bandwidth. Why? Because it's waiting for memory. Okay, fast forward about 10 years. This is data from my own PhD thesis. We looked at applications that Intel used to design their machines with, and we have a similar result. On a system, on these applications, most of the time the processor is waiting for memory, more than 50% of the time. Okay, you don't believe these? Fast forward. Okay, that's the paper. Fast forward about 10 years again. This is a paper published by Google. Google publishers, you should believe it. I'm just joking, of course. But this is a believable number. If you look at these applications that they showed, these are, according to them, all of their data-centric applications. And they basically said processor is waiting for data most of the time, more than 50%. And processor is doing useful work only about 10 to 20% of the time. Okay, and this is actually a beautiful paper. I would definitely recommend reading it also, and they analyze the effect. So basically, I've given you data over the course of 20 years. Nothing has changed. Processor is still waiting for data. Performance has improved, no question about that, but our processors are still very inefficient. So this is because we have a processor-centric design. As a result, we have a grossly imbalanced system. We are violating the balanced design principle. Because processing is done in only one place, processor or accelerators, they're all around that area. And everything else just stores and moves data. As a result, data moves a lot. This is energy inefficient, low performance, and complex. And as a result, we have overly complex and bloated processors and accelerators with very sophisticated memory hierarchies to tolerate data access from memory. GPUs, for example, have very sophisticated hierarchies, massive multi-threading. And as a result, they're energy inefficient, low performance, and complex. As a result, we have the picture that I showed you earlier, right? Most of the system is dedicated to storing and moving data. It's not doing computation. So let's take a look at the energy perspective. That was the performance perspective. This is a slide that I borrowed from Bill Daly, where he shows, you could argue with all of these numbers because they're old numbers, but where he shows the different energy costs of different operations. And I'm going to focus on the 64-bit double precision floating point operation. It's about 20 picojoules. And memory read or write is about 16 nanojoules. That's 800x difference. And I'll take the liberty to make it 3 orders of magnitude over here. Okay, you don't believe 3 orders of magnitude? Actually, let me pull back a little bit. If you go back and do a similar study 70 years ago, when von Neumann was designing their systems, this was not the case. Actually, this difficult operation was about 2 orders of magnitude worse than memory access at the time. This scaled, the logic scaled really well. Memory and interconnect did not scale really well over the last 70 years. As a result, everything moved 5 orders of magnitude to the disadvantage of memory. Okay, so if you don't believe that 3 orders of magnitude, there are a lot of studies that show that memory access costs more than 2 orders of magnitude energy as an add operation. So, and these are some of the most heavily optimized systems in terms of energy. If you want to look at systems that are optimized for energy, you want to look at SOCs. And 2 orders of magnitude is still a lot. Okay, and as I said earlier, we did the study with Google workloads, and we saw that you actually spend more than 60% of your total system energy on data movement. Okay, basically, we don't want to move data. So how do we get there? We need a paradigm shift to enable computation with minimal data movement, compute where it makes sense, where the data resides, not necessarily in memory, not necessarily in storage, not necessarily in interconnect, but in a distributed manner everywhere. Memory is a hard one, that's why we're going to focus on memory today, because the interfaces in memory are actually very difficult to change. Basically, we want to make computing architectures more data-centric, put computation capability at where the data resides or while the data is moving in the interconnect. So this is the example of memory. So if you want to do processing inside the memory, how do we do it? Basically, we would like to put our data inside memory. I'm going to give you the questions over here. Maybe the answers later, but not all of them. So basically, we want systems to query memory, ask questions like, can you execute this function for me? Or please do, and if you get the positive answer, you send the function, and memory executes by itself and returns the results. And then the processor can do more focusing on the results after that point. There are many questions, of course, over here. How do you design the compute-capable memory and the controllers? How do you design the processor chip and the in-memory units? Software and hardware interfaces. We don't have the hardware and software interfaces today to enable this. You cannot talk to memory and software today. No programming language allows you to do that today. Well, the distributed systems programming, you can do it, but memory is not an actor in distributed systems. So how do you design the system software and languages, and how do you design the algorithm? So this is an across-the-stack problem. It may look overwhelming, but we need to start step by step, and I'll hopefully give you some examples of the step by step. But it's not going to be solved at one level, I think. It needs to be solved by looking at across the levels. And there are algorithmic changes that need to be required sometimes to take the biggest advantage of this. So this is an old idea. Again, we don't have a lot of time. I don't want to go into the history of processing in memory, but it actually started in the late 1960s. The first paper is from Harold Stone in IEEE Transactions on Computers, a logic in memory computer. That's the first known paper in the general purpose domain, at least. But it never took off. Why didn't it take off? Because I think there was never a big push from technology, from the circuits and devices. Today, DRAM scaling is difficult, controls are close to DRAM, and industry is open to new memory architecture. So there are things like hybrid memory cube, where you have a logic layer underneath memory layers with very high bandwidth, low latency connections. And Micron actually recently experimented with very simple processing in memory inside the row buffer also. I think there will be more experiments going forward from both smaller and larger companies. And never in the history of computing, we had this big pull from systems and applications. Today, data access is a huge bottleneck. Systems are energy limited, and data movement and energy is much more energy hungry than computation. Now that I motivated this, it was important. Let's go into some examples of how we actually do the processing in memory. I'm going to give you 2 examples, hopefully relatively quickly. How do you minimally change memory chips to do significant amount of computation, and how do you exploit 3D stack memory? So let's start with the first one. So basically, the key idea over here is you can exploit internal connectivity in a memory chip to move data, and you can exploit analog computation capability in a memory chip to do computation. And I'm going to give you examples from DRAM, but this is actually true for emerging memory technologies also. DRAM is just an example that I'm going to use because we happen to work on that area. And I'm going to start with actually something simple, data copy and initialization, not even doing computation. Data copy and initialization today is also very inefficient because it's done through the CPU. But it's very important, clearly it has many, many applications, right? I'm going to skip that data point over there. So how do we copy a source page to a destination page today? Basically, you bring the source page byte by byte all the way into the L1 cache, the destination page byte by byte, do the copy, and then write the result back. So this is high latency, high bandwidth. It causes cache pollution, but you could eliminate that through the DMA engine. And it causes a lot of unwanted data moment. With some technology assumptions, a 4 kilobyte, a small page copy through the DMA engine, not even disturbing the caches, takes about 1,000 nanoseconds and 3.6 microjoules. That's a lot, actually. If you want to actually copy 2 megabytes, multiply that over here. So wouldn't it be nice if we actually gave intelligence to the memory such that we could tell the memory, please do this copy internally without disturbing anything else in the system. This is low latency, low bandwidth, no cache pollution, and no unwanted data moments. And I'm going to show you a mechanism that takes us 1,046 nanoseconds, brings it down to 90 nanoseconds, and 3.6 microjoules to 0.04 microjoules. And the idea is very simple. Most of the functionality already exists in any memory chip that I know of today. Basically, all memory chips consist of this row-based structure. You have these rows, and the rows are connected to sense amplifiers. This is called a subarray. And if you want to have the source row copied to a destination row, they happen to be in the same subarray, what you need to do is actually just 2 activates. That's the idea. You activate the source row, which brings the data into the row buffer. Now the row buffer amplifies the data. It's very strong in the row buffer. Now the next step is to activate the destination row, which implicitly deactivates the source row and activates the destination row. Once you activate the destination row, the strong data over here, strong sense amplifiers, start driving what they've captured back into the array, into the destination row. So by doing 2 consecutive activates, you can copy a source row to a destination row, essentially through charge sharing and sense amplification. Very simple. Today you cannot do it because DRAM manufacturers don't allow you to do it, but this is very, very low cost in terms of hardware. Okay, you can do this between banks and across subarrays also. I'm not going to go into the detail of that. Actually, these are old results. But basically, you can reduce the latency of a row copy, page copy, by more than an order of magnitude, and reduce the memory energy by almost 2 orders of magnitude, because you're not exercising huge interconnects between the processor and memory. Everything is happening inside the memory chip, in the shorter, relatively shorter interconnects over there. Okay, so real applications actually benefit from this also. So basically, what I'm getting at is memory has specialized computation capability that it's very good at. If you can actually minimally modify the chip, you can actually take advantage of that capability. Or if put it another way, memory is similar to a conventional accelerator. We're building all these accelerators that are very sophisticated, but they're all on the wrong side of the memory bus. Why don't we put an accelerator on the right side of the memory bus also, such that it can accelerate these specialized computations? So maybe I cheated. This is copy and initial. So I talked about copy, but initialization is actually a special case of copy. You can think about that. Similarly, we can support and or not. I'm going to give you an example of this very quickly, using analog computation capability of DRAM. The idea is to activate multiple rows concurrently, and that performs computation through charge sharing. I'll give you an example. And you can get 30 to 60x performance and energy improvement, and this was reported in a recent micro paper that we published. I believe new memory technologies enable even more opportunities. These technologies actually fundamentally don't need to move data. DRAM fundamentally is destructive. Whenever you activate a row, you destroy the row. So you need to move the data fundamentally to some place. So as a result, DRAM is not as efficient. Some other emerging technologies can operate on minimum data modes. So let's go into this one. How do we actually do this? So we're going to activate these 3 rows, A, B, C. Imagine these being 8 kilobytes wide. I'm showing you one single cell.
You can run decoder. How do you activate those all?
That's a great question, yeah. We don't want to have 3 decoders.
Yeah.
We want to have this as a special part of the subarray. So when we propose it, it's a special part of the subarray. If you want to do this triple row activate, you directly decode a single line that goes into all 3. So yeah, you're right. If you want to do this as 3 decoders, that's very complex. It's not good. So you need to change the DRAM very slightly to be able to do this. That's a great question, though. Okay, so basically, if you do this activation, what happens is the charge in these capacitors get shared, and in an ideal circuit, what you would get is if 2 of these cells are charged, you get the charge state at the end. If 2 of these cells are discharged, you get the discharge state. In this case, 2 of them are charged, you get the charge state. What is that? That's a majority function. Basically, you have a bitwise majority function by doing this triple row activation. Of course, with Boolean algebra, you can rewrite this bitwise majority function. You can take C out and control C. If C is set to 1, you get the OR of A and B. If C is set to 0, you get the AND of A and B. Essentially, you get bitwise AND and OR. It's both bitwise. You do it 8 kilobytes at a time. And that's one subarray. If you actually have thousands of subarrays in a DRAM chip, you can actually do a massive number of bitwise operations in a single DRAM chip. Okay, AND and OR is good, but it's not functionally complete. If you want a functionally complete system, you want a NOT. This is a bit harder. I'm not going to go into detail, but actually NOT exists. So whenever you activate a row, the complement of it is on the other side of the sense amplifier. It's just not connected anywhere. You just need to connect it back to the array with a special row. This adds a little bit more overhead, but you can do it. Now you have a functionally complete system. Essentially, you can write any program using these primitives, baud, bitwise, AND, and OR, if you spend enough time in the algorithms. This, you can execute anything over here. Of course, some things are easier. So the performance improvement is significant in terms of throughput of NOT. For example, you can get 2 tera NOTs per second, which is much better than GPUs and Intel Skylake in this case. It's much better than the logic layer of hybrid memory cube also, 3D stack memory system. Energy improvement is also significant. You get basically 60x reduction in terms of NOT energy and 25x reduction in terms of XOR, XNOR energy. So you can keep building, of course. XOR and XNOR are not primitives that are directly supported, but you build it through AND and NOTs. Okay, I'm going to skip this over here. I'll give you some applications. So where is this useful? So this is a specialized function, right? You need bulk bitwise operations, but these exist. Databases actually use bulk bitwise operations, bitmap indices. Microsoft has built this bitfunnel engine where they do web search using bulk bitwise operations. Why do they do this? Because GPUs are actually good at bulk bitwise operations today. So they actually want to convert everything to be vectorizable in the bitwise level. That's why they built this web search engine. That's why folks, Jignesh Patel's group built this bit weaving engine. And DNA sequence mapping or encryption algorithms are other examples. I'm not going to go into detail, but let me give you examples of the bitmap. So this is, some databases are built using bitmap engines. You can store the data in this format. For example, imagine you'd store data about all people in the world and categorize by age. It's a huge bitmap, right? If you want to actually search, have a query, say, I want to find all the people between this age range who live in Washington, D.C., who make this much money. It's all bitwise operations. And we can speed up those bitwise operations by 5 to 6x end-to-end if you use this substrate that we call lambda. Okay, people have built databases that take advantage of this also, and we can actually speed up queries by about 12x over here. And the good thing is this scales with the size of the data, because we can actually do many bulk bitwise operations in a single memory module. Okay. If you're interested, the paper has a lot more detail. But basically, we want to have computing architectures with minimal data moment. And I'll ask this question, does memory have to be dumb? Okay, we have one more topic. I'll do it very quickly, and then we'll conclude, right? Okay.
Still waiting for the intelligent controller.
That's it? Oh, okay. So this is, I think, intelligent memory itself.
I see. Okay.
What I'm going to describe is intelligent controller, essentially having a processor inside the controller. That's the 3D stack memory. But I think to orchestrate Ambit, actually, you need an intelligent, you need a controller that has a lot of intelligence. I didn't go over that, but to make it work, your controller needs to be good. Okay, so this was actually part of it, part of the intelligent memory controller. Okay, so let's talk about the 3D stack memory. So this is actually, what I talked about in DRAM, bitwise, AND and OR is a specialized function, right? You don't want to transform all of your algorithms into bulk bitwise AND and OR. It's going to be inefficient, but some algorithms fit very well. But with 3D stack memory, where you have a logic layer underneath memory layers, and memory and logic is connected with high bandwidth and low latency through silicon via connections, you can essentially put any logic inside this logic layer. Think about this as a configurable FPGA substrate, or a substrate that you design just like a processor. And other true 3D technologies are under development that are monolithic that I'm not going to go into. And if you look at this is based on a paper that we published. 3D stack memories are increasing in the field. This is an old paper, it was from 2015. There are going to be more of these 3D stacking that will happen. So there are two key questions here. I'm going to tackle one of them. I'm going to leave the slides for you to look at the second one. So if you have this 3D stack memory, how can we build a specialized accelerator for an important application? What is the architecture and the programming model? What are the mechanisms for acceleration? I'm going to give you the system level without a lot of details over here. And the second question, it's also very interesting, I think, is what is the minimal processing in memory support we can provide in this system such that we don't need to change the programs, we don't need to change the execution model that much, well, we don't need to change the programs that much. We don't need to change the execution model. We don't need to change the virtual memory. We don't need to change the cache coherence that much while achieving significant benefits. I'm not going to talk about this, but this is actually very interesting. You need to introduce instructions that are capable of being executed on the memory side. Let's talk about the first one because it points out to the potential of processing in memory more than the second one, in my opinion. Because here, if you don't need to change much, the benefits are going to be limited. And I'm going to give you the numbers. We actually gain benefits of about 50% compared to existing systems. But with this, I'm going to show you the numbers in a little bit. If you change everything in the system, you get a lot more. And when we started looking into this in about 2013, we basically took graph processing as an important application. It's actually very fundamental. These are based on graphs, but there's a lot of bioinformatics workloads that are based on graphs. A lot of machine learning frameworks are based on graphs today. So graph processing is important and challenging, but making it scalable is also difficult. If you throw cores at the problem, you don't gain much performance improvements. You get a lot of energy inefficiency. Why? Because this is a page rank kernel. This is one example over here. Basically, you get frequent random memory accesses and very little amount of computation. Essentially, you exercise the memory bottleneck a lot. So we built this system based on 3D stacked memory. We call it Tesseract. It's a three-dimensional hypercube. Essentially, you have this 3D stacked memory, and if you look at the logic layer of 3D stacked memory, it consists of vaults. Vaults control the memory on top of them, and these are essentially memory controllers. But we want them to be intelligent, so we actually add simple in-order processing capability. Very simple in-order processing capability. You can think of it as a very low-power ARM core, or even a microcontroller. And we basically, these cores are connected with some network. Actually, networking over here is an interesting research topic also. So if you scale up the system, you actually have these interconnected hybrid memory cube chips also. So what we do is we map graph nodes on top of these hybrid memory cubes, and then we map them on top of the memories of these vaults. So you need to do some intelligent mapping. Whenever we want to do an operation on a graph node, we don't move the data to the in-order core that needs to operate on it, but we move the instruction, operation, to the data. So basically, this is programmed using message passing. If you want to operate on a graph node that happens to be mapped in some vault over here, you send a message to that vault saying that do this operation for me. So it's, if you know the old message passing based systems, it's very similar to those message passing based systems. You have communications via remote function calls, you send messages to the data. And we have some graph processing specific prefetching mechanisms on this. So essentially, what happens is the data doesn't move. Instructions move to the data in this case. Okay, there's a lot of design decisions in this system that I'm not going to go into because we don't have time. But I'm going to give you the results to show you the potential. And the paper is actually very dense in terms of how many. You need to consider a lot of things actually when you design this accelerator. So let's take a look at some results. This is the DDR3 based system, 100 gigabytes per second exposed to the cores. If you have a hybrid memory cube, you get more bandwidth exposed to the cores. And this is the in-order cores, because we can only have very simple cores in 3D stacked memory. Because if you put very complicated cores, you have a thermal problem. It heats up the 3D stack, and you cannot put basically something that consumes a lot of energy over there. So these are 640 gigabytes per second, and this is the Tesseract system. You essentially have 32 Tesseract cores. You get exposed to 8 terabytes per second memory bandwidth in these cores. And this doesn't look like any of these because the processor-memory dichotomy is broken. It's inside each of this you have processor and memory. Okay, so what is the benefit? Average across 5 graph processing algorithms, we get significant performance improvement. It's about 13x, including prefetching. I don't think we optimize the system as much. I believe you can go up to, if you really optimize the system, maybe you can go up to 30x or so. And these are real applications. These are on full graph processing applications with the biggest data sets that we could get our hands on, and we could still simulate. And where's the benefit coming from? Basically, we can exploit 2.9 terabytes per second of the 8 terabytes per second bandwidth. And this also leads to significant energy reduction. It's about 8x energy reduction. And we don't include the baseline out-of-order cores, which we find actually not very energy efficient. So if you're interested, this is the paper. Okay, there's a lot more in this area. I don't have time, I think. Is it time? Or do we have time? Okay, maybe okay, 5 minutes. If you give me 5 minutes, I'll talk about these workloads, because it's also very interesting. So this is changing the entire system, right? If you have this 3D stacked memory and logic, you can redesign your entire system to get 30x. But what if you cannot afford to change your entire system? So that's what we did with Google to understand which part of the workload we can simply offload to the logic layer in a 3D stacked memory plus logic engine. So here we're going to do function offloading. We're going to identify the key functions in some key workloads well, I'm going to skip this. Clearly, energy is important. Some key workloads that a lot of people use, like the browser, TensorFlow Mobile, machine learning inference engine. Even though you don't know that you're using it, you're using it. Your phone is using it. And playback and capture of video. Whenever you look at YouTube, these are active. So we looked at energy cost of data movement in this, and we found out that significant fraction of the system energy spent on data movement. So one solution we examined is moving computation close to data, but how do you do it? So what we did was, you have limited area and energy budget, so we have very simple in-order cores again inside the logic layer. And we wanted to understand the applications. These applications actually have some simple functions that lead to a lot of the data movement. I'm going to give you examples from the TensorFlow in a little bit. And you can design lightweight logic to implement these simple functions inside the memory. You can either do small embedded low power cores, I said, but if you want to be more efficient, you can have small fixed function accelerators. And I'm going to give you results with this. And if you actually do this, and if you do the function, if you offload the right functions to the logic layer, you can improve performance by 55% and energy by about 54%, about 2x basically. So let me give you very quickly an example from TensorFlow, because this happens to be the hot workload, right? You're doing machine learning inference and prediction, and it turns out more than 50% of the inference energy is spent on data movement again. You're moving in and out all of these data. And it turns out more than 50% of the data movement in the workloads that we examined, these are state-of-the-art networks, neural networks, is spent on packing and unpacking of the data such that you can prepare it for the next stage to process, and quantization of the data. So what's packing? Basically, you reorder the elements of matrices to minimize cache misses during matrix multiplication, and it has significant cost and energy. It's very simple data reorganization process that requires very simple arithmetic, so it can be offloaded to memory very simply. We're not offloading the convolutions here, the matrix multiplication, because that's a lot of complexity inside the memory. We keep it in the processor, but these data reorganization operations are very easy to offload. The second is quantization. You don't operate on 32-bit floating point values. You quantize them to 8-bit values today. Actually, people are trying to quantize them to 1 bit, 2 bits today, make it dynamic. And majority of the quantization energy comes from data movement. This is again a very simple operation that requires shift, addition, and multiplication. You can easily offload it to memory. You can actually build a very simple accelerator for it. And we actually evaluated it, and we found out that you can gain significant benefits. You can reduce the energy consumption, but if you use an accelerator, that's a specialized accelerator, you can reduce the energy consumption by 55%, average across all of these functions that I didn't talk about. I talked about the packing and quantization over here. That's true for performance, so you also gain performance. Performance improvement, I'm going to skip these very quickly. These slides will be available, so you can take a look at them. The performance improvement is actually commensurate. You get about 54% performance improvement if you actually design an accelerator inside of it. So it's not clearly 13x or 30x, but it's about 2x if you think about it. You reduce the execution time by 50%, it's 2x performance improvement. But it's significant in my opinion. Okay, so let me go to the conclusion if you allow me. There is a lot more here which is really interesting, but we don't have time for it. Especially the adoption issues are very interesting in my opinion, because we need to do something to adopt. I did intend to skip these slides, by the way. They're there for your benefit if you're interested. So let me actually go through here. This is the fun part. Say again?
Post-conference talk.
Sure.
Like you again after the conference.
Yeah. Well, so hopefully this is interesting. But let me conclude. I think basically there is some famous architect who said this: architecture should be based upon principle, not upon precedent. Precedent is what comes before. Principle is principle. Anybody guess who this is? Frank Lloyd Wright. Okay. How do you know this?
I used to live in Oak Park, Illinois, where he had a studio.
Oh, okay, cool. That's great. You knew that he had this quote, or you guessed based on the quote that it was his quote?
It sounded like something he'd say.
Yeah, exactly. He was a hard-headed architect, and he did a lot of great works, actually. And if he were designing based on precedent, he would have designed something like this, which is not bad. It's livable. It's like the architectures that we have today. But it's clearly not like this. This is something close to my heart. This is close to Pittsburgh. Falling water, right? This is a masterpiece. It has a lot of beautiful characteristics, which we're not going to go into because we don't have time, but it's based on some principle, which is organic architecture, which is a principle he subscribed to. He has the best examples of organic architecture, the best early example of organic architecture, right? Basically being in harmony with the nature. Right? If you look over here, these cantilevers over here imitate how this falling waterfall is constructed actually. That's one example. Okay, now that I'm in Zurich, I use this example. This is a train station all over Switzerland, all over Europe. It's functional, it works. It's boring. It's based on precedent, so you basically stamp out the same design everywhere. But it's nothing like this. This is a Stadelhofen train station in Zurich. When you enter here, you see something different. This is in Lisbon. It's based on some other principle, the same principle actually. This is Valencia. Can anybody guess what this is? It's not a harp.
This is Calatrava's work.
It's Calatrava's work, exactly, yes. This is Sevilla. It's a pigeon actually, according to him. I kind of empathize with it. Okay, I'm going to skip the Barcelona one. But maybe you empathize with this one more. Does anybody know where this is?
New York.
This is in New York, yeah. This is the Oculus, essentially. And this is Calatrava's work, as you said. He was an ETH alumnus in civil engineering, PhD in civil engineering. This is $4 billion, according to the website Forces. And it cost a lot to New Yorkers. It caused a lot of pain. It's new technology compared to the other regular train stations, right? So in order to move to the new technology, they had to pay a lot of cost. But now, if New Yorkers or other people go inside it, they don't care about the cost because the transition to the new paradigm has been accomplished. Basically, this is based on some other principle. So the question I have is, do we have the principles for computing? I don't claim that I have them, but I know that processor-centric design is not the only principle with which we should design computers. There should be more. So in my opinion, it's time to design principled system architectures to solve the memory problem. We have a huge memory problem that we've been avoiding as much as possible. As a result, we have imbalanced, completely imbalanced systems. Our systems are imbalanced, but we should design complete systems to be balanced, high performance and energy efficient, which I believe requires being data-centric. We should be able to process data where it resides. We can call it memory-centric also. We need to enable computation capability inside and close to memory, but also in other places where data is stored and where data is moving. I believe this can lead to orders of magnitude improvements, as I showed you examples of, enable new application and computing platforms. I'd be happy to talk about this. We're doing a lot of work in bioinformatics, for example. You have to have processing in memory if you want to actually process a lot of data. And I believe this could enable better understanding of the nature also, because I don't think nature operates on processor-centric principles. And maybe other things, who knows. So I think regardless of challenges, the future of processing in memory is bright, but we need to pay the cost. So you cannot have an Oculus without paying cost for it. So whenever I give this talk, usually cost is one of the arguments that are brought up. It's true, any new technology requires cost. You need to be ready to pay the cost for it. Otherwise, the cost of other things may be too much, right? But once you pay the cost, actually, you transform and you exploit the technology. But to enable it, we actually need to think across the stack. We need to think across different layers. And I think there's hope. Let me take one more and we'll be done. So we've been very successful with one technology that has revolutionized our lives. And that actually came from electronics and memory. Can anybody guess what that is? Okay, it's late, so I'll call it flash memory, SSDs. This thing wouldn't exist without flash memory. But if you go back 30 years ago, flash memory was a very doubtful emerging technology. People I know, used to write proposals to NSF saying, oh, I'm working on garbage collection for flash memory. This is going to be the biggest technology. And they would get rejected. Who cares about this technology? Flash memory, what is it? It's actually true that technology didn't work. Most of the bits in flash memory don't work. But people designed whole systems and infrastructures, and they paid a lot of cost to make it work. And as a result of that, we can write papers like this that talk about the sophistication of the controllers that we have in flash memory today. And more importantly, we can enable technologies like this. And I think that's true for processing in memory also, which of course may be more difficult than flash memory, even more difficult. But we need to actually look into it and need to pay the cost for it. And if you're interested, we actually written this longer paper that talks about some of the adoption challenges and some of the issues that we see in terms of processing in memory going forward. Okay, that's where I'll conclude. I'd be happy to take more questions.
Maybe 5 minutes or 10 minutes.
Sure, yeah.
We should.
Yes, please.
Yeah, so I mean, this is really very nice to say that processing should be done on memory. Can you also give us some insight? The data is moving so fast that memory may not really be able to keep up, and we need to explore to get right for other media. So, what do you think is future like?
Yeah, absolutely. I think I picked the example of memory there because that's what we work on, but processing really needs to be distributed across where the data is. So I believe it has to be done where the storage, hard disks are, where the SSDs are. I think those are slightly easier because you almost have a system inside the SSD today. You actually have the flash translation layer, you have ARM-based controllers, you can actually push some computation close to there. So in my opinion, all of those components that store data need to be more intelligent, have processing capability. I picked processing in memory because it's a harder interface. And also I think the network controllers also, there's a lot of data movement that happens in the network. And the data has to move for some reason, right? Sometimes you cannot, if you need to communicate, you need to move the data. And if you have computation capability in the controls and the interconnect, that will also provide benefits. Yes?
Thinking up on that, do you have an idea of the quantitative benefit of doing more processing in memory? Like, are we talking, what percentage of workload in current applications is actually amenable to this kind of?
So that's a great question. That's a question that we're answering right now. We actually have some work where we are analyzing, I think we've analyzed more than 350 applications across many different domains to understand where are the data movement bottlenecks. And we see a significant fraction of those applications are bottlenecked by data movement between memory and the processor. This is an ongoing work. I can tell you about it maybe next year when the work is done. So it's a hard question, of course. There are some applications that are very good at utilizing the caches, and I think they should not move to memory. That's why processing should not just be in memory, processing should be distributed. And there are some applications that don't utilize the caches really well at all. And it's heterogeneous, it's intermixed across the application also. There are some functions that you should really put into memory because they move a lot of data uselessly otherwise. So you need to have a methodology for figuring out which functions should be executed in the memory or the processor and guide the programmer. Ideally, we would like to do this automatically, but I think it's very difficult to task automatically. So the first step we've taken is understanding the applications, figuring out the methodology to understand which functions are more amenable to processing in memory versus in the processor, and then guiding the programmer to actually participate in the application.
And in the long term, that probably would change the practices of the programmers if you had those capabilities.
Exactly. That's why we wanted to start with this workload-centric approach. So hopefully I'll be able to present it sometime next year. But that's an excellent question. Yes?
A slightly related follow-up. Could you comment a little bit more on your opinion about software interfaces in the future? Will we have compilers and runtime systems that can use these devices, or as programmers we will always have to do something in our applications?
So I think that's a great question. You know, that's why I put this entire stack picture. It's not just a programmer. I think initially, once we start having computation capability inside memory, the real ninja programmers will program and they will take advantage of it, just like how GPUs came about. But actually, GPUs are a good example, right? GPUs have a compiler and runtimes, and increasingly they're going to be more sophisticated. I think processing, it's going to happen for processing memory also. Actually, we've looked at some of the works that I skipped over there are looking at compiler support to automatically extract functions that are suitable for processing in memory. We gain some benefits. Of course, it's not as high as 13x again. But I think over time, that support will come about. And I think it's nearly necessary to help the programmer to take advantage of the underlying substrate.
Good question for you. When you said 67%,
Yes, 62%.
is that memory activities, or did you take a different activity?
So that's a great question. So actually, it's all of the energy that are caused by data movement across the memory hierarchy. So it includes the interconnect. It includes all of the data movement energy. So we didn't just say DRAM energy. It includes, actually, most of the energy comes from the interconnect because you're moving the data. Actually, if you look at the DRAM chip, most of the energy is interconnect also. Because exactly, they're all in the column.
So you did account for the
Absolutely, yeah.
for the wiring.
Absolutely, yeah. Yeah. If you want to reduce energy, you want to reduce interconnect energy. That's the biggest impact, actually. So there was this HPC panel, I think, in 2002. I wasn't there, but I read the slides. Is it the memory or is it the interconnect, right? In my opinion, it's a moot question because memory and interconnect are so coupled together that it's both.
Well, thank you very, very much for listening.
Oh.